we return to a situation of deep and abiding interest. Start with a polynomial ring in a single variable x over some field f. We want to intimately understand quotients of this polynomial ring by non-trivial ideals. What's so great about this quotient ring? We'll see in a bit that it allows us to magically create roots of polynomials out of thin air. Okay, now this polynomial ring is a principal ideal domain. So every non-trivial ideal is generated by a polynomial of positive degree. I can make this polynomial monic by dividing by the leading coefficient, and then the generator g becomes unique. Here are two basic questions about this quotient ring fx mod g. How big is it, and when is it a field or a domain? I have repeated here the answers to these questions that I wrote at the end of last lecture. But this time I have also included an explicit basis that I had asked you to discover last time. So now that you know the complete answers, pause now and do these questions for yourself. They are easy enough to do quickly and so important that you need to own the answers. So pause right now and do them for yourself. The first exercise is just an observation using long division. What is important is that it is worth making and remembering. For the proof, we have to show existence and uniqueness of such a representation. So, let's take a congruence class in here and suppose it is represented by some polynomial h. Now, we can do long division of h by g because g is monic and get a remainder r. Now, this equation shows that r and h are equal modulo g. And now the polynomial r is of the required type because it is less than g. Uniqueness is also easy because any multiple of g will have degree at least n. And if I take two representatives of this type, distinct ones, then their difference will be a polynomial of degree strictly less than n, which cannot be a multiple of g. Okay, so this proves the first statement. In the second one, I am saying that congruence classes of 1, x square up to x to the n minus 1 give me a basis of this quotient ring as an F vector space. But the question is, how is this ring a vector space over F in the first place? This is not difficult, but formally it needs to be answered. So just take a moment to think about it. Only scalar multiplication has to be defined. I multiply a congruence class by scalar A by multiplying any representative in the ring. And you can do the routine check that this works. With this, the second statement is just a reformulation of the first. Okay. Now before we go to exercise 2, I want you to consider the following. If I replace the field F by an arbitrary commutative ring R, then how much of this stays valid? So please check this now. Rx need not be a PID, but if I restrict myself to going modulo a principal ideal generated by a monic polynomial, then everything works just as before because I can still do long division by this monic polynomial. Here I have just replaced every f with r and you should check that this works. For now, ignore this second statement. Here I need a change of language. I cannot say vector space because R may not be a field. In the definition of a vector space, if I replace a field with an arbitrary ring R, then I get what is called an R module. This quotient ring becomes an R module exactly the same way as before. And then the statement is that this quotient ring, when G is a monic polynomial, is a free R module with the same basis as before. This is interesting because in general, modules may not even have a basis. But you can ignore everything about modules for now and remember just the first statement, which is equivalent to this second one. This statement is quite useful even for general rings, but for us the most important case is when R is a field. So let's return to that and do exercise 2. We want to know when the quotient ring fx mod g is a field or an integral domain. Of course, Any field is a domain, but here for a non-zero polynomial g, even the converse is true. And these two things happen precisely when g is an irreducible polynomial. Let's see why. First, a simple remark about principal ideals in any ring. AR is a subset of BR exactly when A is contained in BR, but that just means that A is a multiple of B. In other words, B, the generator of the bigger ideal, is a divisor of A, the generator of the smaller ideal. We will use this mainly when B is a non-zero element in an integral domain, in this case fx. So let's see how the remark helps. Fx mod g is a field exactly when the ideal generated by g is maximal. That means that any ideal containing this one is either equal to it or the entire polynomial ring. Now, this containment by our observation is just saying that d is a factor of g and I can take d to be monic. Then this statement just becomes, if a monic polynomial d divides g, then d has to be either equal to g itself or 1. But that's just the definition of g being irreducible in fx. So I have shown the equivalence of these three conditions. It is important to say in fx because we may be talking about more than one field at a time. For example, x square minus 2 is irreducible in qx, but it does factor over r. Okay, so all this when g is irreducible. But what if g does factor non-trivially? Try to relate it to fx mod g being a domain and then try to see the equivalence of all 5 statements. So please do this now. Such a factoring tells me that the congruence classes of h1 and h2 are non-zero, but their product is 0 in this quotient. So fx mod g is not a domain. Therefore, if it is a domain, then g cannot have factored. That is, it is irreducible. But therefore, fx mod g is a field. So I get 4 equivalent conditions and a fifth one because r mod I being a domain is equivalent to the ideal I being a prime ideal. I have shown here all the equivalences. A small but important note. All this works only for non-zero g. If g is 0, then I just get the ring fx itself, which is a domain but not a field. Said another way, 0 is a prime ideal but it is not maximal. However, in the special ring fx, every non-zero prime ideal is maximal. You should pause here if necessary and fix all of these conditions in your mind, including the reasons why they are equivalent. Taking fx modulo irreducible g is going to be our favorite method to construct new fields from given fields. And then exercise 1 tells us something basic, the size of this new field. These facts are not hard to remember. For example, you can keep in mind the parallel case of integers. Z mod nz has size n and it is a field exactly when n does not factor. But the interesting thing about fx mod irreducible g is that this gives me many new fields. So this construction is going to be absolutely foundational for field theory. We will use this all the time, starting now. So please do exercise 3. If t square minus 5 factored non-trivially in qx, it would have to be into 2 linear factors, and therefore the polynomial would have to have a rational root. But it does not, and therefore it is irreducible. So this quotient is a field. Next, t cube is not divisible by t square minus 5. Therefore, in the quotient it is non-zero and hence an invertible element of this field. To find the inverse, for convenience, first I have expressed it in terms of this nice basis using long division by t square minus 5 and I get 5t. Now, I have found the inverse of 5t by this seemingly ad hoc calculation. So please check this. Next, the answer is in terms of this basis, and therefore when expressed like this, it is unique. But the question is, how do I do this calculation systematically? I have phrased this as a general question here, and you should be able to do this quickly. So please do this now. I should always remember that I have long division over fx. So by Euclidean algorithm, GCD of any two things can be written as their linear combination. G is irreducible, so its GCD with anything can only be 1 or G. But H is not divisible by G. So the GCD has to be 1, and going modulo G in this equation, I get the required inverse. Next, I have changed the polynomial to t cube minus 5, but I claim that I still get a field, this time of dimension 3 over q, because this polynomial is irreducible. I would like you to justify why. If you said only that cube root of 5 is irrational, then that is not enough. All roots of this polynomial are irrational, but it does factor over rationals. So this is something special about degrees 2 and 3. A non-trivial factor of any polynomial has to have degree strictly less than that polynomial, and also cannot be a constant because units do not count. So, if a polynomial of degree 2 or 3 factors non-trivially, one of the factors must be linear, and therefore such a polynomial must have a root in f. So, for a degree 2 or 3 polynomial to be irreducible, it is enough to check that it does not have a root in the ground field. T cube minus 5 has all of its roots irrational, and so therefore it is irreducible. Next, I have asked you to construct fields of cardinality 4 and 8. These remarks may help, but you need to figure out which field to start with. So try that. If I start with fpx and go modulo a polynomial of degree n, I get a vector space of dimension n over fp. So the cardinality of this ring is p to the n, because coefficient of any basis vector can be chosen in p ways. So if I want a field of size p to the n, then it's enough to look for an irreducible polynomial of degree n in fpx. Now we'll see in chapter 15 that for every prime p and every degree n, there is such a polynomial. But in the given small cases, we can just look. For cardinalities 4 and 8, I should start with f2x and look for an irreducible quadratic and an irreducible cubic. Okay. Now, of the 4 quadratic polynomials, 3 of them factor and this one is irreducible. So, I get a field of cardinality 4. For cubic polynomials, to check irreducibility, I just have to ensure that there is no root. And you can check that there are exactly 2 possibilities. So going modulo them, it may seem that I get 2 fields of cardinality 8. However, you should check that they are actually isomorphic. In fact, more is true. For every prime power, there is a unique field up to isomorphism of that cardinality. We'll see this in chapter 15. But for these small numbers, I have asked you to check that there is indeed a unique field up to isomorphism of that size. Okay. You should also see some examples over F3. And finally, I have asked you to classify up to isomorphism all rings of cardinality 4. Okay. This exercise is very interesting in that its argument will use most of the concepts that we have seen so far. But it's also not hard. There aren't very many such rings, so I strongly recommend this exercise. We've hammered again and again that going modulo an irreducible polynomial in fx is great. So let's summarize what we know about such polynomials over various fields. Over a general field, I cannot really say much, but I do know that all linear polynomials are irreducible, and for degrees 2 and 3, it is enough to check that the polynomial does not have a root in f. For specific fields, I can say more. For complex numbers, I know that every polynomial factors completely. So only the linear polynomials are irreducible. Over real numbers, besides the linear ones, The only irreducible polynomials are quadratics with negative discriminant. All other polynomials factor. This is because a polynomial of odd degree has a real root because of intermediate value theorem, and all non-real roots come in complex conjugate pairs, and each such pair gives me a factor of this kind. Next, over rational numbers, irreducible polynomials require serious study, and we will get a taste of this in chapter 12. Going modulo these polynomials gives me fields that are called algebraic number fields, and they can be realized inside complex numbers. In case of FP, we have already seen irreducible polynomials of small degrees over F2, and you should do the same for other small primes. In general, I can count such polynomials of any given degree n over Fp, and going modulo such a polynomial creates for me the field of order p to the n, as we will see in chapter 15. Finally, I have the field of rational functions f round bracket t, which is the fraction field of the polynomial ring. We will not really study irreducible polynomials over this field. Going modulo them gives me what are called function fields, and they are important in algebraic geometry. Okay, you should try to fix this table in your mind because it summarizes what we know at present about various fields and irreducible polynomials over them. So please do that. Looking at this table, especially these two cases, should tell us that we need to study factorization more seriously. That will be our next topic. But for now, let's learn the language of attaching elements. It is particularly useful for field theory, but can be defined for general rings. So let us see that. Let's see what it means to adjoin or attach an element alpha to a ring R. This is equivalent to just talking about quotients of polynomial rings. But the new terminology is quite useful, especially in field theory. I can attach an element concretely where alpha is an already existing element in some larger ring S. Or I can attach abstractly where I have to create the element alpha satisfying desired conditions. So let's make the definitions carefully, starting with the concrete case. In this situation, I define R adjoined with alpha to be the set of finite sums of elements of the type something in the ring times a power of alpha. You should check a few things quickly. First, this set does form a ring. It is the subring of S generated by R and alpha. So the smallest ring containing both of these. Next, this notation is consistent with the old notation because the polynomial ring is obtained by attaching X to R. I can generalize this construction to the case where I am attaching a finite number of elements of S or even an arbitrary subset of S to R. Okay. Next, try to relate R adjoined with alpha to the polynomial ring by substitution principle. Pay close attention to the situation where the kernel of this map is generated by a single monic polynomial. Extend the identity map on R to the polynomial ring by sending X to alpha. This homomorphism phi evaluates any polynomial on alpha, and it is surjective. Therefore, by the isomorphism theorem, R alpha is isomorphic to Rx modulo the kernel of this map. Now, if this kernel happens to be generated by a single monic polynomial of degree n, then I know a very nice basis of this quotient ring consisting of powers of x up to n minus 1. So, by this isomorphism, I get a nice R basis of R adjoined with alpha consisting of powers of alpha up to alpha to the n minus 1. I will always be in this situation if the ground ring is a field and the kernel is non-zero, because any non-zero ideal of fx is generated by a single monic polynomial. Often the situation is even nicer. Both R and S are fields. In this situation, I make two cases about alpha. If the evaluation at alpha map has no kernel, then such alpha is called transcendental over the ground field. And if this evaluation map does have non-zero kernel, then alpha is called algebraic over F. So explore both of these situations and say the maximum that you can about the ring F adjoined with alpha in each of these cases. If the kernel of the evaluation map is 0, then it is an isomorphism onto its image. So all powers of alpha form an F basis for it. In particular, the dimension is infinite. If the map phi does have a kernel, then it consists of all polynomials having alpha as a root. This ideal is generated by a unique monic polynomial, let's say g. Then g is called the minimal polynomial of alpha over f. And the degree of this polynomial is also called the degree of alpha over f. In this situation, the dimension of f alpha over f is also equal to this degree, as we saw before, and we have this nice basis. In particular, the dimension of f alpha is finite. Now, we can reverse both of these arrows, because if the dimension is finite, then alpha cannot be transcendental because the dimension would have been infinite, and vice versa. Another interesting point. So far, we have never used the fact that all of this is happening in a field. Because E is a field, the subring F alpha is a domain. Try to see what this says about the minimal polynomial G and the nature of this ring. If a polynomial G factors non-trivially, then this quotient ring is not a domain, but it is isomorphic to F adjoined with alpha, which is a domain. Therefore, the minimal polynomial G must be irreducible. But in that case, I know that this quotient is actually a field. Therefore, F adjoined with alpha must also be a field. The converse is also true, because if this is a field, alpha cannot be transcendental, since I know that the polynomial ring is not a field. This entire situation is very basic for field theory, so you must know it extremely well. By that I mean the following. Suppose I have a field extension, that just means one field containing another. In this situation, for an alpha in the bigger field, you should know very well all characterizations of alpha being transcendental over F and also the characterizations of alpha being algebraic over F. In the algebraic situation, you should also know this entire picture that goes along with it. To fix this in your mind, it will be helpful to write down as many examples as you can. And we have seen a number of them. So try to write them down. And in each situation, also try to write down the minimal polynomial and also this nice basis. So do this now. This is mostly seeing old examples in new language. I have already seen the first two. I still have to prove irreducibility of x to the n minus 2 over rationals for general n, but I have already done this over here. It is a standard but difficult fact that pi does not satisfy any rational polynomial. So pi is transcendental over q, and this subring of complex numbers is isomorphic to the polynomial ring over q. The over q part is important. If I do the same thing over real numbers, then pi is already real. So attaching it just gives me back real numbers. Pi is algebraic over real numbers of degree 1. Next, I have attached a non-real cube root of 1 to real numbers and I get complex numbers. This final example is also old, but it doesn't quite fit yet in our new language. So you should think why and see what can be done about it. The point is, to adjoin alpha to F, I need to have in advance an E that contains F as well as alpha. Here, I don't have anything that contains F2 in advance. So I created it. Now, the congruence class of T has this as the minimal polynomial over F2 by construction, and this new field can be thought of as F2 adjoined with T bar. But for that I have to expand my language, where what I am adjoining need not be given in advance. This is done by attaching an abstract element. So let's see that language. Suppose I don't know any numbers beyond integers, but I still want to have a number alpha whose cube is 2. No such number exists, but I can create it by taking zx mod x cube minus 2 and defining alpha to be the congruence class of x. Just check that this works. If I subtract 2 from the cube of alpha, I get the congruence class of x cube minus 2, and that is 0 because I made it so. Similarly, the quotient construction allows me to adjoin alpha to any ring R with whatever polynomial conditions I want. Therefore, this construction is just another way of talking about quotients of polynomial rings. But psychologically, it is interesting because it gives a new way of thinking. However, you should be cautious in applying this construction in full generality, because it may give surprising results that are contrary to your psychological expectations. For example, the natural map from R to R adjoined with alpha may not be injective. I have given an example here. Attach alpha and see what you get. Watch what happens. 2 alpha is supposed to equal 1. So squaring, I get 1 equals 4 alpha square, but 4 is 0. So in this ring, I get 1 equals 0, and after attaching alpha, the entire ring collapses. In fact, this is not even a ring according to our definition. You can and should check this more formally. For that, this method from last time may come handy. You can impose two relations one at a time or both at once. Using this trick, you get this isomorphism, and now all I have to check is that the ideal generated by 4 and 2x minus 1 is the entire ring because it contains 1. For this last check, the first calculation can be a useful guideline. Okay, what happened here is an instance of a general phenomenon. When I impose a relation, it can have knock-on effects. So why did the ring collapse here? Because you can say that 2 is a zero divisor here, in fact nilpotent, and I tried to invert it. Instead, if I am going modulo a single monic polynomial, then I know how big R adjoined with alpha is. In fact, I know a nice R basis. This will always be the case when R is a field F, because in Fx, every non-zero ideal is generated by a monic polynomial. But even here, you need to have right intuition. See what happens in this example. Rx is a PID. So, no matter how many conditions I put on alpha, they will be generated by a single monic polynomial. But here I already have such a polynomial. So, let's see what happens. X cube minus 1 over real numbers factors into x minus 1 and x square plus x plus 1. They are relatively prime. So, by the Chinese remainder theorem, I get this isomorphism. Now the first term is isomorphic to real numbers by sending x to 1, and the second one to complex numbers by sending x to a non-real cube root of 1. So I get R cross C. Okay, now you might ask, real numbers already contained a cube root of 1. So why doesn't this construction give me back real numbers? But first, it's the wrong size. Going modulo a cubic polynomial should give me something of dimension 3 over R. But more conceptually, this condition makes no distinction between the 3 cube roots of 1. So the answer has to accommodate all 3 of them. Okay, if I work over F3, then over there, 1 has a single cube root, but it still comes thrice in the answer. These kinds of situations are quite useful. For example, in analyzing canonical forms of matrices over fields. But the attachment construction really comes into its own when I am going modulo an irreducible polynomial. This construction is then quite crucial for field theory. So let's see that situation. We return to the situation of central interest. Take a field F and an irreducible polynomial g over that. Going modulo g, I get a field that contains f as constants. I can regard this field as f adjoined with t bar, where t bar is a root that I created for g by the magic of the quotient construction. In fact, the minimal polynomial of t bar over f is g of x. Notice that I am using different letters for the variable in the polynomial and the root that I created for that. In practice, people often use the same letter and this could lead to confusion, so watch out. Okay, what's so good about this construction? We already saw that for FP, it allows us to create larger finite fields without having a home for them in advance. Okay, but more is true. We will see that this construction allows us to study roots intrinsically. To appreciate this, consider an example. X cube minus 2 has 3 complex roots. The real cube root of 2 and that multiplied by omega and omega square. Now, if I adjoin the real cube root, I stay within real numbers. But if I adjoin a non-real root to Q, then I go outside real numbers. Nonetheless, I claim that all these three fields are isomorphic to each other. So do this as an important exercise. This is so simple that it's easy to miss the point. Take the evaluation homomorphism from Qt taking t to alpha. Now t cube minus 2 is in the kernel because alpha is a root of this polynomial. Can the kernel be any bigger? If so, it would need to contain a polynomial that divides t cube minus 2. However, t cube minus 2 is irreducible over q and therefore it generates the entire kernel. And this map is an isomorphism. Now, whatever I said about this ring applies equally well to both of these. Therefore, all three maps are isomorphisms and therefore these three rings are isomorphic to each other in a very specific way. Namely, all roots of this irreducible polynomial get matched up with each other. So, somehow this quotient ring captures the essence of what it means to be a root of this irreducible polynomial. Such a root may have different concrete manifestations, but this description is intrinsic because of the way this ring is constructed. Okay, I have abstracted out the general principle at work over here in this very important exercise, which you should do now. Here is another exercise about the concrete situation over here, and you can try this on your own. The backward direction is more interesting. Alpha and beta are roots of the same irreducible polynomial. We want a map taking alpha to beta. But this is just like what we did for x cube minus 2, and you should check that the same argument works. So, what is being said is that a root of an irreducible polynomial can be sent by a ring homomorphism to any root of the same polynomial. Okay, the forward direction is easier and it is based on the simpler principle that a ring homomorphism must take a root to a root. So you can check the details over here. This last exercise has a very similar proof. It is a very useful result at the foundation of Galois theory. It may look a bit complicated, but it is really answering a very basic question. So try to understand the statement. The situation is easier to visualize with a picture. Everything is a field. F is contained in E and alpha is an element algebraic over F in some field. We want to know how many homomorphisms there are from F alpha to E that are identity on F. The only way this situation is different from here is that now alpha is allowed to sit outside E. But the reasoning stays exactly the same. Alpha has a minimal polynomial over F which is irreducible. Now, alpha has to go to a root of the same polynomial in E, and alpha can go to any root of that polynomial in E. Therefore, the number of such ring homomorphisms is the number of distinct roots of the minimal polynomial of alpha over F that are sitting in E. It may be useful to keep an example in mind to remember this result. So, take F to be rational numbers and alpha to be cube root of 2. Now, if I take E to be real numbers, then alpha can go only to itself, and so there is only one such homomorphism, namely inclusion. But if I take E to be complex numbers, then alpha can go to any one of the three roots of x cube minus 2, and therefore there are three such homomorphisms.